Hello, we're Team 3 and we're analyzing and redesigning a manual juicer. A manual juicer is a simple mechanical kitchen appliance that extracts juice by compressing fruit through a strainer using a linkage mechanism. Similar models sell about 85,000 units per year. Our model is a linkage-based design with 12 unique parts excluding fasteners and can be seen assembled on the left and exploded on the right. Small businesses such as cafes, bars, juice stands, and restaurants are the primary customers since they use presses daily. Secondary customers include health-conscious individuals and travelers and campers who want affordable, non-electric juicing solutions.
The fast diagram here shows that the primary function of the juice press is to extract fruit, with secondary functions including pressing the fruit, straining the pulp, and ensuring the product is dependable and convenient. Using our component list and functions from the fast diagram, we created a matrix to define the component functionality. The main function shown in the diagram is to convert power. This includes components in the linkage system, revealing opportunities for both manual and automated assembly.
Here you can see the bill of materials for a hand-pressed juicer. After estimating material, processing, assembly, and tooling costs, the total cost came out to be $79.28, so our product sits at about 65% of retail price of a comparable hand-pressed juicer. The cost of each part from the bill of materials and the importance based on the function component mapping matrix were used to classify the parts for redesign consideration.
Now we will discuss the product family design. For this, we compared the functives on our fast diagram with our primary and secondary customer groups to determine what would be different. For this, we would determine two different functions would be different: collect pulp and assure convenience. This is because the primary group will be using the juicer for longer extended periods of time. To help with this, we wanted them to have the ability to collect more pulp in the reamer funnel without having to empty it every few uses. And we also wanted a redesign of the handling to be a more ergonomic design that promotes extended use.
The design for manual assembly focused on link B right and link B left and the central shaft as platform parts and the reamer funnel as the module part. From the quad chart, the parts that are both high cost and high functionality leave limited room for modification without compromising part performance. Instead, we chose to focus on parts where assembly time improvements would be most impactful and feasible. These selected components offered clear opportunities to reduce part variety and increase part symmetry, as shown in the leftmost image of link B right and link B left. To reduce part count, as shown in the center, where we combined the funnel base with the reamer funnel. And finally, to add features for easy insertion, shown in the final image of the central shaft, where we added chamfers on the top and bottom of the shaft. The modifications made allowed for assembly time improvements from 90.76 seconds to 85.76 seconds, and an assembly efficiency improvement from 19.83% to 20.99%.
The linkage assembly was chosen for automated assembly due to its small, lightweight parts. Link A is also a high-cost, high-importance component, making it a strong candidate for redesign. The juicer contains two of these sub-assemblies, meaning any improvements have a large overall impact. An exploded view of the original subassembly can be seen on the left, consisting of Link A, Link B, a washer, and a screw. The profiles of Link A and Link B are shown for clarity on the right. Using design for assembly principles, we simplified the assembly process. A surface was added to Link A to remove the need for the washer and reduce parts. We removed the curve in Link A to maintain minimum part variety and added flat edges to both links to improve automated orientation. These changes keep the same functionality while streamlining assembly. However, they could increase part manufacturing cost. Before redesign, the automated assembly cost was $4.07, driven by handling, feeding, and insertion costs across the four parts. After redesign, the cost decreased to $2.45, primarily due to part elimination and easier handling. Therefore, the redesign resulted in a 40% reduction in automated assembly cost.
To select a manufacturing process for the redesigned funnel, the selection chart shown was used. Based on various factors such as material shape, mass, section thickness, tolerance level, surface roughness, and batch size, the team found that both die casting and machining were viable process options. The team selected machining as the manufacturing process due to the part's low batch size and upfront cost.
Analyzing the new funnel component, we estimated the cost of machining per part to be $11.52, with a material cost of $5.92 per part, a setup cost of 44 cents per part, and a significant feature cost of $5.16 per part. The outer diameter of the funnel head is 78 millimeters, and the minimum diameter of the funnel base is 15 millimeters. Our team quickly noticed a few features that contributed to the high feature cost of this machined part. First of all, the filleted outside edges and drafted walls are difficult to machine and require a significant amount of material to be removed. Second, the fillet along the internal face of the funnel is 0.5 millimeters, which is unnecessarily small. Finally, the two through holes have different diameters, requiring additional tooling. After running the component on DfM Pro, we were given the recommendation to use chamfers on the outside corners as opposed to fillets. After taking into account these considerations, the team heavily redesigned the component. First, a rectangular body was adopted over the original circular one to eliminate the need to remove non-functional material. The outside fillet was replaced with the chamfer, and through holes were set to the same diameter of 17.5 millimeters. Finally, the inside fillet was increased from 0.5 millimeters to 2 millimeters. With these changes in place, our team then reanalyzed the component and found the cost of machining per part to be $9.26, with the most significant cost reduction being in the feature cost. By following DFMC rules, we were able to reduce the cost of each part by $2.26. While our hubs quote is relatively inaccurate due to significant extrapolation, as the platform could only handle quantities up to 11, which is much less than our expected quantity of 85,000 annually, we can still see the same trend of cost reduction through the revisions our team made.
To select a manufacturing process for the redesigned Link A, a selection chart shown was used. Based on various factors such as material, shape, mass, section thickness, tolerance level, surface roughness, and batch size, the team found that only die casting was a suitable manufacturing process for the part. It is important to note that if the part had a lower batch size, for example, if it only used one part in each mechanical juice press, then the link could additionally be machined.
To analyze Link A for manufacturing via die casting, the chosen parting line shown in the top right corner was chosen. From this, a cost of die casting per part was found to be $1 a part, with the material cost being 31 cents, the operating cost being 56 cents, and the die cost being 13 cents. The original part had a minimum thickness of 3 millimeters and a maximum thickness of 10 millimeters, a volume of 67.5 centimeters cubed, a length of 19 centimeters, and a width of 3.5 centimeters. Since DfM Pro was not available for die casting, the DfM principles outlined in the die casting lecture were used. Following these, we wanted to target the sharp edges along the side of the link and the non-uniform thickness and change these to be better suited for manufacturing. Following the DfM principles, 3 changes were made to Link A to better suit it for die casting. The first change was decreasing the radius on the top and bottom of the link to help decrease the wall thickness. This was following the DfM principle of uniform thickness. Change 2 was the addition of chamfers on the edges of the link to help decrease sharp edges, which is following the design principle of avoiding sharp corners. Change 3 was the decreased thickness of the center shaft, which followed the design principle of uniform thickness. With these changes, the overall part thickness became uniform at 6 millimeters. With these changes, the cost of the die cast was refound to be 94 cents per part, which is a reduced cost per part of 6 cents.
A product service system for the mechanical juice press is the Juice Optimizer app. It supports users with seasonal fruit recommendations, curated recipes, nutritional estimates, and expected waste outputs. Users can also order ingredients directly from local grocery stores. This creates new revenue opportunities through subscriptions, promotions, or purchase commissions, while improving the customer experience by putting recipes, nutritional info, and shopping all in one place. It additionally helps reduce environmental waste by encouraging seasonal and right-sized buying. In conclusion, for DFA improvements, we have a 5-second reduction for the manual assembly and a $1.62 assembly cost reduction for the automated assembly. For DFM improvements, we have a 6-cent piece price reduction for Link A and a $2.26 piece price reduction for the funnel. While our design reduced the cost for assembly and manufacturing, the team believes that the height between the funnel and the base should increase to allow larger cups or pitchers. An additional approach, if we had more time, could look into redesigning and reducing the cost of the base.